Hello, hello everyone, and welcome to the Java to the Java Code Camp. So if you like coding, you've come to the right place. So in these sessions of Java coding live, we're going to be learning and we're going to be coding live together. We're going to be answering questions, learning new concepts, and everything there is to know about coding. So about coding in functional programming. So as some of you know, my name is Matti. I'm a subject matter expert here at Globant. I'm based in the UK, and I'm going to be teaching you for four sessions, 4 weeks. We're going to be learning about functional programming and some concepts about functional programming and everything that you have to know to improve your coding style using functional programming in Java. Also, let me do a brief recap of what we did in last session. So, in last session, what we did was we went over the building blocks of functional programming. So, these building blocks, as we saw last week, was types, values, functions, expressions. When we start using these building blocks, some patterns arise. Like when we start using object-oriented programming and we have some design patterns, we also have some design patterns that we can use in functional programming. So I'm going to be teaching you about these um, design patterns that we have there and how we can use them in Java as well. So if we can move to the slides. All right. Um, and I'm going to give you a jargon alert because I'm going to be using some weird names. So don't worry about these names. These are just names that come mostly from a theory in mathematics called category theory and group theory. So there's nothing to worry about. I'm going to explain everything to you, but yeah, just giving you this jargon alert. All right. So to start talking about the patterns that we have in functional programming, I want to introduce one pattern called the optional pattern or the maybe pattern. And this is a pattern that we want to use to avoid the $1 billion mistake. So, Sir Tony Hoare introduced the concept of the null pointers in ALGOL, and the whole family of languages of ALGOL languages inherited that concept of null pointer, and Java, being one of its many grandchildren, also inherit the null pointer. So in Java, we can create a variable and we can assign it to null. And Sir Tony called this his $1 million mistake. And we Java developers know what it is to have the null pointer exceptions everywhere, not knowing when it can appear, and having to safeguard every part of our code, checking if this is null, then do this. If it's not null, then do that. So we always have to check for nulls and that kind of things. So the optional pattern arises as an alternative to null, to the null pointer. Um, so optional is a concept that we borrow from functional programming languages, and it represents the possibility of a value not being there. Okay, and why do we have this? In functional programming, one of the things that we always try to do is define functions for all its inputs, right? So let's look briefly at this function that we have right here. We have this function called divide. It's a very simple function. It receives two doubles and it returns the division of those two doubles. So this function here says that it receives two doubles and returns a double, but actually there is also a different thing that could happen here. If y is a 0, then there's no return. There's going to be an exception because we cannot divide by 0. So this here is a more it's a more precise way to define the function. We have, in this case, the possibility of not being a result for this, and we represent this with an optional. So this optional, we've used it in our last week session. We've been using it, and we were saying like, okay, optional, we can use it. We use it when we may not have a value to return. So in this is what it represents: the possibility of that value not existing. Because we cannot divide by 0, we return an empty optional, which is basically no result. And that is one of the advantages of using optional. Let me show you an example of what we did last week. All right. So we have here the shortest path function, and we see that this returns an optional. And actually, before that, let me just, I'm going to share the repository that I created last week. I created a repository in GitHub, and I'm posting it in the chat window uh, for all of you to download if you want. So so you can follow along, and you can open the code. I mean, if you didn't have the code from last week, then you can take a look at the code in that GitHub repository, and we can go on from there. Let me know if you got that. All right. What do we have here? So all right. So we were talking about optionals. So this is returning an optional path. Instead of returning just a path, we're returning an optional path because we do know that because we have a condition, there might be a path, there might be no path that fulfills that condition. So what we say is, okay, if we don't have any path, then we want to represent that possibility. And instead of returning null, like we would do in Java, usually, we're just returning an optional. And this gives the user or the function the ability to handle that possibility by themselves. Because if we throw an exception, for example, then the user doesn't. Sometimes they don't know if we use unchecked exceptions, for example, the user might not know that the method throws an exception, and they may want to handle the exception as a business logic. So this way they can handle the business logic, um, and in a more in a better way, let's say. And you see, um, when we return the optional, the optional is in a signature, so it's very clear what we are returning. We're not returning a path that might be null. We're returning something that the user knows that might not be there. That is the great thing about this, compared to just null. Because if I were to just return null, for example, and this would be just path, then the user may not know that this path can be null, right? Um, let me know if you got the. I think the GitHub repository was not shared, so I'm going to share it with someone that can also paste it in the chat window. Uh, yeah, there we go. Let's see if they can share it. All right. Um, so we were talking about optionals. Going back to my presentation. So if you look at this, um, all right. So we have optionals now. This is how the code could look without optionals. So we have a parameter, and we get if we had to check if it is null, and then we can use that parameter. In this case, because we have an optional, we cannot forget to check if the object is present or not. So that's an advantage. It's you have to check. You have to check if it is present or not. But other than that, I don't see a great advantage of using optional with just this. And this is why we want to introduce some other patterns where we can see the real power of this optional and other patterns. So, as I told you before, these some of these terms come from a theory in math called category theory, and it's basically, I'm going to be very quick with this and just go to what we care about. Basically, category theory studies how um, things are connected and how you can compose things. And in programming languages, we have one category, which is the category of the types. So we have integers, we have strings, we have classes, we have all the types. And we are interested in how the types are related between each other. And how are they related? They are related with functions. So if you have a function that takes a parameter, that parameter has a type, and it returns and it returns something, and that something has another type. So, for example, we have the function to string of integer, and we can and this turns an integer into string. All right. Because we do this, we know that integer is related to string with the method to string, and then we also have string double, and we can transform this string into a double with the value of function. So this thing is how they are related. But now we have optionals, and it feels like we are losing that ability to relate integers with strings and with doubles, because now we have an optional integer. So how do I turn an optional integer into a string? How do I do that? Because I want to do that. And or how do I turn a string into a double, an optional string into a double? So here's when we had to introduce the pattern called functor. This pattern here, we can basically turn this optional into another optional type using the map function. So we've used it in our code. Let me show you. I think here we've used the map function before. We used it, instead of using it for optionals, we used it for stream, but it's the same. Let's see if we can quickly do an example. We have, for example, our path test. Sorry, the path list test, right? And remember that this test gives us a, as a result, an optional, right? Let me show you how we can operate with optionals as if they weren't optionals. That's the cool thing about the functor pattern. We want to operate with it as if it wasn't an optional, as if it was actually an object. It has a value. So if I do map here, it it takes a function as a parameter, map, right? So what does the map function do? It's a higher order function. Remember we talked about this last week? These are functions that take other functions as parameters. So if I do this and I say, for example, path, and I want to get the distance from the path. So I can say path distance. I can even make it shorter with method reference. And if I put this into a variable, let's name it distance. You see what happens? The type of the optional of the response is now an optional of big decimal. You see how we operated with the optional as if it wasn't an optional, but then we get an optional in return. That is the magic of the functor pattern. And that is why we use the map function. It's because we want to operate with things as if they weren't optionals. Another example that we saw last week was using map with we used map. Where was it? Here with streams, right? So what does this mean? This means that we want to operate with segments because we have a stream of segments. We want to operate with segments as if it was only one segment instead of a stream. And that's why we use map. Map allows us to keep the structure, these relationships that we have here. The function map allows us to keep that structure and we can operate with things as if they weren't optionals or streams or whatever. That's the beauty of the functor pattern. Um, so here's another example where you see here we have to check for null, and then if it is null, we return a default value. But with optional plus functor, we can operate with it as if we as if it wasn't, and we can also handle the scenario in which it actually the value doesn't exist. So in this case we use the or else method to return the default value. And you can tell me, but I think this syntax over here is way more clear than this one, where we have this if and we have to check for null and all that. So I'm going to stop for a moment and see if you have any questions on the chat regarding what we're just talking about. But if there are no questions, then I can go on. Uh, it seems like there's no questions. All right, guys, no questions about the optional pattern. And by the end of this session, we're going to be using this pattern, the functor pattern, the optional pattern, for a new feature on this code. So don't worry, we're going to keep working on this. All right, let's move on. Now I'm going to introduce a different pattern called the monoid. And this comes from group theory. Basically, a monoid imagine we have a binary operation. What is a binary operation? An operation that takes two parameters and returns something. So if we have a binary operation like the addition of two integers, for example, we can we can add these two integers. But if we have three integers, how do we add them? Like, how do we add three integers? Because addition is only works for two, right? But fortunately, we have some rules that allow us to apply to do the addition of three numbers. What we have to do is first add two of them, and finally we add the last one. So, for example, if we have a plus b plus c, we can do a plus b and then plus c, or we could do b plus c and then we can do plus a. And this is called associativity. And I'm sure that all of you know this from school. And so, what what we have defined using the integers and the the binary operation, like the addition and the associativity property, and we also had to add in the the identity element, which is the element that doesn't modify the result at all, which in addition is zero. If we add all that together, we get a group, which is also called a monoid. And and we can do this with classes as well. We use this pattern in programming when we want to do aggregations, for example. And we have actually used this pattern in our last episode, in our last session. So if we look at it, let me show you. You see here, we are using this function called reduce, right? In this function, let's look at the signature of this function. And what does it take as its signature? Surprise, surprise, a binary operation. All right, so this means it takes an integer, it takes two parameters and applies it to the function. And it's called accumulator. But basically, a binary operation takes two parameters and applies it to each other. And this in this case, the parameters have to be the same type. All right. So reduce, we've used it. Why? Because we wanted to add all the distances for our path. For our so we had all the segments and we wanted to add all the distances. So we are adding it here with the reduce method. And if you see, this reduce here is applying the monoid principle, because what it's saying is I'm going to apply this binary operation to a list of things, not just two. Make sense? We're not using just two segments here. We're using many, and because it's a binary operation, what we do with reduce is basically we accumulate the value and we keep adding until we have added all of them. That's why we use this for aggregations. And it gives you a very clear syntax. Because we have this reduce function here, we can very clearly understand what is happening here. Remember in the last session I showed you how we would implement this on a imperative approach, where we do a for loop and we have a, a variable accumulating everything. That is also a monoid, but it's implemented in a way more imperative and less declarative. In this case, this is very, very declarative because we're just saying apply this binary operation to this list, and that's it. Um, and because this these binary operations and this distance are associative, we can do this very easily. All right, let me go back to my slide. And there's something else here. If we notice, there is an option in the reduce operation that returns. In this case, it returns an optional. You see, but we can also have another signature. We can also have another signature where we set the identity. So in this case, the identity is the object that doesn't modify the result, and it's used in the case of the stream being empty. So if I were to, for example, in this case, I'm returning zero, so I'm having the identity value here, but it's a bit shady. So if I move it here, for example, and I say big decimal zero, now I have the identity here, and you can clearly see that this is using the monoid pattern. So it says, if you have nothing, use zero. Otherwise, just keep adding. Very clear. Right. So any questions regarding the monoid? Doesn't seem like there are any questions so far. So I'm going to move on because the next pattern is very, very similar. It's very related to this one, and it's called the map reduce pattern. Basically, sometimes we have classes or we have data that are in itself are not monoids. So we want to create a monoid so that we can operate with a binary operation like an aggregation. And when I mean aggregation, it's not just additions. It could be an average. It could be I mean, whatever. It doesn't come anything comes to my mind now, but it could be anything, any binary operation that could be applied to two objects. But there are things that are not we're not able to apply binary operations. Like how do we apply binary operations to segments, for example? It doesn't it doesn't seem right. So that's why we have to we have something that we would like to operate with, but it's not we cannot operate with it very in a nice way. So we use the map function that we saw before with the functor pattern. We use the map function to transform our non-monoid objects into a monoid object. And we saw this with the distance method. So in the distance method, we effectively use the map reduce operation, the map reduce pattern. So you see here, and it's really easy to identify in this case because we're using the map method and then we're using the reduce method. So it's extremely clear. But there are some languages where this function might be called differently. It's not called reduce. It's called it could be called aggregate. It could be called different things, and also with the map function. Sometimes there's not even a map function because of some languages uh, you have just the syntax sugar that means the map. But in Java, it's very clear. Like we're using map and then reduce. So we're using the map reduce So this is what we were talking about. We couldn't operate with segments. We couldn't add segments, but we can add big decimals. So we turned it into big decimals, and then we have a monoid that we can operate with. And that's a great thing about this. And this pattern in particular is heavily used in anything related to data analytics. I mean, this is the pattern in which Google was built in, and many data analytic tools have are prepared for to use this pattern. Um, so it's really really important. And what I like the most about this is how nice it looks compared to something done in an imperative manner. Um, let's see. All right. So I think we, I think it was clear. The monoid, the sorry, the map reduce pattern. I don't know if there are any questions. Um, but yeah, it's simple. It might sound scary. All this concept might sound scary, but it's really simple. Uh, you just need to understand what's going on, and that's it. There's a question saying, "Are we going to implement these patterns?" Oh, actually, so if you look at the code from last session, we actually did. We implemented some of them, but there are a few things I'm going to do by the end of the session, where I'm going to be adding a new feature to our code. So yes, we're going to be using more patterns, and it's going to be interesting. So yeah, yeah. Thanks for the question. All right. So let's talk about monads. And this is another scary word from category theory, which it shouldn't be that scary. Um, but yeah, let's see. We have monads is a pattern that allow us to add effects to our functions. So we have in functional programming this concept of pure functions, right? And these pure functions are great because they're easy testing. It's really useful. Like the code looks great, and it's really easy to understand. But we do have to, for example, provide an output for our system. We have to write something somewhere, and that is not a pure function. We have to, I don't know, write things in a log. We have to, I don't know, throw an exception, return an error sometimes. And these kind of things are not pure. These go outside of the pure function concept that we have in functional programming. So, functional programmers introduce the concept of monad to help with the ability to add effects to our pure functions. So, you remember when we talked about the optional pattern, we said optional represents the possibility of the object not being there, which is in itself a side effect. So that thing is is an effect that then we have to handle at some point. We cannot go get our get our way doing map and map and map and map and not handle the possibility of the value not being there at some point. So monads, and the worst thing is that when you have many things that could be not there, like we have many optionals, and how do we handle that? Like, how do we handle the fact that we have, let's say, two values and we have to operate with them, but they are optionals? So how do we handle that? And that is why we have monads. we want to compose those effects. Like we want to compose the possibility of not being there in a value and not being there in another value. And I know this might sound uh, crazy now, but I'm going to add some examples that it will be very easy to understand. Let me, all right. So formally, a monad has two functions. It has the unit function to create the monad without computation value, like the creation of the, like in optional we have optional empty, that is the create function. And then we have the the bind function or the flap map function. And you may have heard of flap map because we used it in our last session as well. Flap map is actually the method that monads give you. We talked about map before, and that is great. But now we're talking about having two optionals or two streams, and we want to operate with them. So how do we operate with things that might not be there? We use the flap map operation. So in Java, we have three built-in monads. So we have stream, we have optional, we have completable future. Stream is used to process elements of a collection and apply a pipeline of transformations. And it is a monad because it has the flap map method. And what we did with the flap map method, remember, basically we we got rid of one collection layer. We went to we had a collection inside a collection, and we wanted to flatten it, and that is where the flat map name comes from. It flattens the collection inside the collection into a single collection. With collections, it's easier to see. It might be harder to see with optionals, but it's the same concept. And I'm going to do an example later. Um, mhm. So optional, we saw it represents the possibility of the value not being there, and then the the flap map allows for the composition of many optionals. So let's say I have a function that returns an optional, and then with the value of the optional, I want to operate into another function that will also return an optional. How do I do that? And how do I keep the values? How do I keep the value in a way that in the end I only have one optional, not many? That's why I use flatmap. And then complete of a future, it's um, it's another it's another monad, and it doesn't have the flatmap method, but it does have the then compose method, which is the same as flatmap. So completable future is a monad that it's a structure that is used in Java to create asynchronous tasks. I don't know if you heard about asynchronous tasks, but basically asynchronous tasks are a way of running things in the future without waiting for them to happen. Like, let's say I want to run many calculations, but I don't want to block my main thread, like in a UI, for example. If I have a UI, I have my main thread where the user is clicking things on the phone, for example. You can see this in Android or in JavaScript as well. Um, when you click on things, you don't want to block the screen for some computation going on in the background. So that's why you use complete of the future, for example. You can basically complete of the future will run in a different thread, and this will make the application not be blocked. That is great. And but there are cases where a future operation will also call a different future operation, and that's how you want to then flatten the completable future into a single future. You don't want to have two futures to operate with. You just want one, because you have one and then you call the second one, but then you get as a result only one composed task. Uh, what is the advantage here is that completable futures have different issues that could happen in the background. So you need to handle all those effects. Like for example, if the task didn't finish for some reason, um, if there was an error, an exception in the task, in the future task, anything that could happen in the background, you want to compose it all into a single uh, monet, into a single structure. You don't want to deal with many things at the same time. That's why we use then compose. Um, by the way, I'm going to be digging way deeper into completable future and stream in the next session. So don't worry about it, because there's a lot to unpack there. And so let me show you an example of monad composition. Um, let's say we have a function here, and we have this other function, this private function here, and it returns something that could be null. All right. So the parameter could be null, so we check for null here, and then we get this. We call this function here. If it wasn't null, we call this function here, and then we have to check if r is null, and then at that moment we can use r, and then if for some reason the first one was null or the second one was null, it's going to end up here and return the default value. How do we do this with monad composition? It's really simple. We change here, we change the signature. Instead of returning null, we will return an optional. And because we're returning an optional, and we have an optional to begin with, what we're saying is, I'm going to assume that my parameter is not null with the flat map, like we did with map, but in this case we're going to be using flat map. Why is that? Let me show you an example here. Um, if I uh, um, let's go to our path list test. I have an optional here, right? Optional path. If I do map, and let's say I have a function here, uh, optional big decimal, right? Yeah, distance. This it doesn't have to make sense. It's just for example. But if I do this and let's say return 10, sorry, big decimal 10. Oh, I had to return it as an optional. Right. Now, if I call this function, I have this map here, and I want to operate with the path as if it was present. And then I say get distance. Let's see the result type for this. You see what happens? I have an optional big decimal, because this thing returns an option as well. So how do I avoid this? If I use flat map, see what happened. The type changed to just optional bit decimal. What we are doing here is we're saying only if path is there, operate with this. And because we took care of the effect of the path not being there, we don't want to have an optional of an optional. We just need to get the last optional. So that's what we're doing here. And then I can just simply do or else and return a default value, whatever I want. Let's say big decimal zero, for example, and that would be my default value. And that in that moment, I am handling the case in which the object doesn't exist. Okay, so going back to my presentation, um, that is what we call monadic composition. So we don't have to handle the effects of the big decimal not being there or of the pad not being there. We combine those effects together into a single optional effect, and that's the power of it, and that's why I like it so much. Um, and I think it's clear. I mean, you can tell me in the comments or wherever. You can tell me if this is clearer than this or not, but I believe this is way more clear and aesthetic and understandable. Um, all right. So monads are functors as well. So we're using the map uh, function. So we said that, and monads are functors as well. And these functors are combining side effects together. And so notice that the flat map operation combines monads and return a new monad. It's a binary operation basically, right? So we're combining these monads into a single one. And we can do this as much as we want. So we could do another flat map and another flat map. So we can apply that binary. It's a binary operation. The flat map is a binary operation of monads. And we also have the unit to create the monad. So everything sounds like it's a monoid, right? Because we have the we have the ability to reduce these side effects into a single one, and we are dealing with we have one our identity value, and we have our binary operation. So everything tends to be a monoid, and that is the full definition of a monad. I mean, um, because the monads are a functor and actually are something called an endofunctor because they operate with the same types. I won't go deeper in that, but monads are endofunctors. What we say is that a monad is a monoid in the category of endofunctors. So basically, a monad is something that allows you to combine side effects for your program, and that is the beauty of it. So, woo, that's crazy. Yeah, you have to take some time to let all that sink in. But yeah, it's a great concept, and the good thing about Java is that we do have these things already available for us to use, but we don't have to keep it like that. I mean, we can also use we can also create our own monads, and that is something that I really want us to do uh, probably in the next session. So now, as I promised before, let's write some code because yeah, I love writing code. I didn't want this to be just a presentation. Let's write some code. I'm going to add a new feature. This new feature is going to be really interesting. Um, I'm going to have a list of public transports. Sorry. Yeah, I'm going to have a list of public transportation, and I'm going to have them combined with the paths. So we have a list of paths, and we want to get the shortest path, and then that includes some points, and then I want to see the public transportations that we have for those paths and say, okay, I want the shortest path, but I also want uh, to take the bus. So give me all that. So what do you think? It's going to be interesting, right? Um, any questions so far? I think by implementing this feature is going to be more clear for you. So let's start with let's start with the public transportation class. I'm going to create a class called public transport. It's going to be a record. Sorry, no, I like records for functional programming. And inside this, I'm going to also create a enum public transport type. And we could have like the bus, we could have train, tram, underground. That should be fine. All right. So what is this public transport is going to have? So basically, we could say that a public transport has a path, right? Because they follow a path. If that makes sense. So I could reuse my class path here, and I will also add the public transport type here. Okay. So I'm going to switch the order because I like it better to type first. All right. And what do we want to do with the public transport? We want to figure out if the transport works for a given path. Okay, so if I have a path and I have a transport, I want to see if that transport can be used for that path. And I'm going to implement this in a very simple way because I don't want to go into a lot of details. Um, but I think we can reuse, and this is going to be a very simple implementation. Well, it works for path, right? So, and now what do? We create a test, right? Let's create one public transport test. And let's do test as works for path. It does. So um, let's see. I'll get a path example from our path test here, and I'm going to create a new path for a transport path. and I'm going to let's see, I'm going to add some more segments to the transport path. Say we have 10. This is one, let's say here like this, and then I'm going to add here, let's say, and 10 again. In this, it's going to be, sorry, 10, 1, and 10. Okay. And so now we have this all fine. I'm going to create a public transport of the type bus and with the transport path. And this is going to be my implementation. It's going to be really easy. I'm basically going to say if my transport path includes the paths in my path, then that's fine. Then that should work. Um, Sorry, it has to include the first path, sorry, the first point and the last point. That's what I want. Because if I do that, then if my path, if my transport includes the first path and the last path, at the last point, then my transport eventually will get me there. So just for the sake of our testing, I'm going to add here another path. No, let's just for the first test, let's going to do this. And let's say when and only 2 points in path. Okay. So I want this to be true. I want this to, because this transport includes these points, the first point and the last point. Then I want this to be true. I'm going to say public transport works for path. And if I run this, it fails because I don't have a return statement. Okay, it doesn't work. So I will have to implement some things in our path class, which I have already implemented in the background, which is this method here, first and last point. So I have a method here that will return the first and the last point of my segment of my path. So how do I do this? I'm saying return path. Actually, if I just say true, this will work, but that's not what we want. I'm going to say return path includes points. No, sorry. Yeah, includes points. So the path in this public transport has to include some points, and this is something that we implemented last session. Remember the includes point function. So now we have this includes points, and we can say the path we receive. Oh, that's the problem. We have path here and we have path here. Let's say let's just rename this to how do we rename this? Path, photo path, a path. I don't know. You can come up with a better name than than me. Um, let's see, a path. So the path. this path. Oh, other path are saying there in the comments. I like that one. Let's just rename it. Other path. Yeah, that's a good one. Thanks. Other path. First and last point. Okay. And with first and last point, I'm going to yeah. Okay. So these should already work, but let's just test it because we're using functionality we already created. So basically, it's going to work. Just to make sure it works for the scenario, for example, um, in which, for example, doesn't include when it doesn't, let's say, doesn't. So this is the last point here. So I'm going to take out that one here. Let's just say 0, 0. So that one will not be included now. And I should say here I set false. And this should probably work. Oh, it doesn't. It could be. What could be going on here? We have 0, 0. Oh, right. That's because I'm lazy. Let's just say new big decimal 1000. That should work. Oh no. Uh. All right. This is interesting. Let's go here. Let's take a look at what's going on here. What is going on? I'm going to debug. This is live coding, remember? Uh, uh, what's going on here? So we have 0, 0 and 1, 1. And my path, if I say path dot um, 0, 0 and 1, 1. Yeah, it is included. Did I change the wrong test? Let's take a look. Oh yeah, I think I changed the wrong test. No, no, I didn't change the wrong test. Uh, um, let's make it really obvious that it doesn't include it. Because I think because I'm being lazy with the test cases. I'm just removing this one. 0, 0 is included. 0, 1 is included. 0, 0, 1 and 1, 1. And we have pathless here. Sorry. So let's run the test again. No, this is not the test, sorry. Dun, dun. Public transportation test. Yeah, now it works. Yeah, I was just being lazy with the values I was using. I wanted to use all the constants here. All right. So now that we know this works, we have to do one more scenario in which we don't care about the middle points. For example, if we add a middle point here that is obviously not included, for example, uh, actually I'm going to use as a template the first test because we know this is included. So if I add a middle point that it's obviously not included, it shouldn't, it should disregard it. If I add a segment here, I'm going to say these points here. I'm going to say new big decimal 100 and 200 200. So this should still work. This is with three uh, segments, and it works. All right. So everything is working now. Any doubts or anything that we have implemented so far? All right. So I'm going to move quickly and create the public transport list. This class be a record, and it's going to have a list of public transports. Right? And public transports. And in this class, what we are going to do is we're going to implement a method, and I have the signature for this method here. This method is going to find a public transport for a type and for a path, right? So I'm going to also create a helper class that represents the path with the transport because I want this to return a path with a transport. It's going to have a path and it's going to have a public transport. Oops. Public transport. And I'm going to implement this method. Oh, creating a test. Void test find first transport and type. Uh, Transport for type and path. So, where is this? In our previous test, we created public transport test. We created a public transport, so I'm going to use that. Uh, uh, Public transport. And to be honest, we had to be careful with the code we use for testing. I'm being rough here because I had to move fast, but uh, really we have to be careful and maintain our testing code base as much as we maintain our production code base. So I'm going to create a method for get public or just public transport, create public transport, and this is in the test, remember, and I'm going to return this. And I'm going to create another method, helper method, that returns a path. Create path. Okay, so I have um, so let's see. I have the transport list, new transport list, public transport list. I'm going to say path here. Sorry, um, going to receive a list of public transports. And so new, so create public transport. I'm going to keep it just one. And public transport list, find first, and I'm going to say bus, and I'm going to say create path. So the path that we created, and this returns an optional path with transport. Okay, and this should be present. So true optional is present. Okay. So now if I go here and I want to do the implementation, how would I do this? I would say transport stream, and then I want to filter. So I'm going to filter, and I have two conditions. One, that is the requested type, for example, bus, and the other condition is that it works for the path. So I'm going to create two predicates. The first predicate is requested. Actually, yeah, let's just say here uh, the transport. Let's go, oh, no, here transport is going to have type the type it's equals to the type sent as a parameter, and we can extract this into a function so that it's clear, like this. Sorry, like this. And this is going to be is requested type. So this returns a predicate. You see? And now we can compose predicates. And transport E works for path. And then we want to find the first one. So find first, and what else? Now we want to return the path and the transport together. So I'm going to say map, like we did with the functor pattern, because we have an optional, but we have to map it into something else. Map t and new path with transport. We send the path and the transport that we just found. And remember, this could not be here. Like this transport could not be there. So that's why we use map, because we want to operate as if it was there. And now if we run the test, there's an error somewhere. I had to say return here. If I run this test now, it works. Brilliant. What do you think? It's getting there. So now we have just one more piece of functionality and we are done. Um, we'll create something called the path service. And this path service is going to basically print the path. So this is like our top layer. It's going to this is not going to return anything. So here we're handling the side effects of our program. Just like our program is pure functions, top to bottom, except for this part. And I'm going to um, so and I cannot write it. I won't write a test for this because I want you to see the side effect here. Um, so here's what I did. I have a path list. So I find the shortest path in the path list. And remember that this returns an optional, right? So let me show you quickly. This is a path, optional path. This returns an optional. So now I want to use this method, which also returns an optional. So here we see monad composition. Remember the monadic composition we saw in the slides? Here we are using it. All right. So I'm going to, and um, there are ways in which we can test this, but since I want to go quickly with this one, I'm going to do it in a different way. Because trust me, there are ways. Like I could return something different here, like an optional string, and then print it on my test or something like that. But I want to treat this as if this was my top layer. So what's happening here? I have this optional and I want to operate with this optional, and then I have another method that will return an optional. So I have to use flat map so that this thing here will compose both into the same optional. So it will compose the side effect of the values not being there. If I would use map here, look what happens. I have an optional of an optional, so that doesn't work for me. I want to flatten that effect. All right. So and I'm declaring this variable so that you can see, but actually what I would do is not declare variables at all and just use it in a fluent API way. So basically here, see, like this here. So have shortest path, then flat map, and then we can handle the effect. So we can say, for example, if present or else, and we can send two functions to handle it. So the first function is going to say, um, so path with transport, and we're just going to print it. System uh, just going to print the path found for the transport was. And because records already have a toString, we don't really need to implement the toString method. That's great. And this if present or else receives two actions basically. The action when the value is present and the action when it's not present. When it's not present, we have to send an action that it takes no parameter. And in this case, we're going to say, we're going to print there was no path, no, no path found for that public transport type. Okay, so now we can, um, I'm going to create quickly a main here, and I'm going to use the same methods to create the path and the transport that we use here. Where are they? We have so many classes now. um, Path service. I'm going to put them here as well, but we obviously need to reuse this in a better way. We're not doing this in the proper way. We're just testing now and running a POC. Um, so I'm going to say new path service. I'm going to create, this should be static. And this should be static as well. I'm going to say create path, create public transport. I'm going to create a new public transport list. And now I'm going to call the path service. Fine. And so we have we have a list of points that we need to include. So let's put let's put these points that are in the path. Sorry, the points should be, let's say, these two. Then we have, I'm going to put this in a variable. So I want this to be neat. So we have the points. Then what else do we need to send? We have the path list. I'm going to say, I have to create a path list here. So new path list. And this path list here, I'm going to put it here, rename it list. Then we have the public transport list. And finally, the public transport type. Right. So if I run this, we should see in the standard output that there was a path found for our public transport type and so on, and our points and everything. That's great. Then we can also, for example, like we could change the list of points so that the path won't be there. Big decimal. So now, in the first step, it's going to return an empty optional because the path is this point is not in the path. So the first step is going to return optional. It's going to return an empty optional. So you see, there was no path found for that transport type and everything. So if I go back now, I could change, for example, the public transport list so that this is going to fail. This is going to return. Is going to return the optional empty. So, for example, actually, I don't have to change it. I had to just ask for a different type, like for example, underground. If I use underground, I don't have underground here in our list. So if I run this again, empty. So you see, we have merged or we have combined the effect of the values not being there, and that is the power of monadic composition. So this was the end of our presentation, but I don't know if you have any questions so far for me. Let's see if you have any questions on the comments. Um, and I hope I don't know. Have you enjoyed it? Did you like these patterns? Did you like how they are all related together? I find it fascinating. When I first discovered this thing, I was like, wow, this is great. Uh, but yeah, I mean, it's really good. So if there are no questions, guys, I would like to thank you all for joining, for staying to the very end of the stream, and um, yeah, just thank you for being here, and I'll be waiting for all of you in the next Thursday session, where we are going to be learning even more about the inbuilt design patterns, and we will also implement our own monad. So that seems promising, right? All right. Thank you, guys. Have a good day.